electrons right next to each other. This is a proton, this is a proton. And then down here, I've got a proton next to an electron. So this is a proton, and this is, let's make that plus a little better, and this is an electron, okay? Now, what's going to happen with these two protons near each other? Well, you might have heard the expression, like charges repel each other, where opposite charges attract. If that's the case, it is the case, then what's going to happen when these two protons get near each other is there's going to be a force pushing them away from each other. Okay? So if I just have two lone protons, nothing else, they're going to try and push each other away with a certain amount of force. So we represent force with a capital F. And down here, likewise, this proton and this electron, these are opposite charges, so they're going to attract. They're going to want to be near each other. Okay? So what is that force going to be? What are the things that are going to impact that force? Because these things have such little mass. It's not like there's a gravitational pull here. It's not like these things are actually tethered together. These aren't physically touching. If the electron were to physically touch the proton, they would actually merge and become a neutron. It'd be ridiculous. We don't want that to happen in our atom. So there is a force that binds electrons to the nucleus of the atom. And that force is defined by something called Coulomb's law. Coulomb's law looks like this. We have a K, a Q1, a Q2, and an R squared. It's a square right there. So let's walk through this problem. Let's walk through this equation. First off, this K right here. What is this K? Well, what's happening here is all of the things that we use to measure this stuff, like we use newtons for forces, we use coulombs for charges, and we use meters for radius. We made those measurements up. So they don't always jive that well with how reality actually works. So sometimes we need a modifier. And so K here is just a constant. It's called the Boltzmann constant. And it's like pi. It's just a number. It's not going to really come up. We're not going to have anything changing about K, so we're not really going to need to worry about it. So just pretend it's not there. So then, what about these Q's? What are these Q's doing here? Well, these Q's are going to represent charges. Let's write that, charges. And this is going to be, Q1 is going to be my first thing. Q2 is going to be my second thing, whatever that thing might be. We could have a balloon that has a bunch of charges on it being attracted to a wall that has the opposite charges on it. This is what happens when you rub a balloon on your hair and your hair sticks to the balloon. So whatever thing that is, we're tracking the charges between those two things. And then this R right here, this R, that is going to be a radius. And so we measure a radius in meters, but we call it a radius because, technically speaking, this proton right here, it could have charge interactions with anything that's a certain distance away. If we say it's 1 meter away, let's say this is 1 meter away, well, this could be 1 meter away, this could be 1 meter away, that could be 1 meter away, same thing up here. And so if we kind of track all the way around, it really forms a field of a circle, which circles have radiuses. So that's kind of the rationale for using radius there. But notice that this is divided by radius squared. So as something gets farther away, so if we say that this is 1 meter away, well, divided by 1 squared equals being divided by 1, right? Well, let's say we go twice as far away, to 2 meters away. Well, then that would be divided by 2 squared. Well, divided by 2 squared is actually divided by 4. So just going twice the distance away, I'm actually 4 times the division. That's going to be pretty significant. So the protons are going to push each other away. In fact, the only reason protons stay together in the atomic nucleus is because the neutrons are there to hold them tight. So let's look at some atoms here. I've got these two drawn out. I've got a lithium atom and I've got a sodium atom. And so my lithium atom here is going to have a certain number of protons, right? How many protons does a lithium atom have? It's going to have 3 protons. And a sodium atom, likewise, it's going to have 11 protons. So if I want to look at what's going on for this electron right here, this electron is going to be attracted to that nucleus. It's going to have a certain distance. Let's call this distance from the nucleus, let's call that 1. Let's just call it a 1. So if I put that into Coulomb's law, which let's write that over here again, Q1, Q2 over R squared. If I plug those numbers in, well then my Q1, this would really be my Q1, and then my Q2 would really be the charge of that electron. This would be Q2. And that charge on that electron would be negative 1. Be negative 1. Okay. So what if I get farther away? What if I go here? Well, if I go there, I'm going to have a very different distance. So Are my protons going to change? No, my protons aren't going to change. Is the charge of my electron going to change? No, of course not. This is still just one electron, so this is still going to be -1. So if we were to compare the values here, then we could say this first one, it's a unit of 1 away. It's really 3 times -1, so 3 times -1 divided by 1 away, so 1 squared, which would just be 3. We use absolute values for Coulomb's law. So I'm not worrying about that negative. So this second electron, well, that's going to be a distance of, well, I'm sorry, it's going to have a charge of 3 for that nucleus. That's going to stay the same. Charge of -1 for the electron, and it's going to be divided by, well, now it's going to be 2 away, 2 squared. And so that's going to be 3 times -1. Absolute value is 3 divided by 2 squared, which is 4. That's going to be 0.75. That's pretty significant here. So that's a pretty significant drop-off. Now what about down here? How does that compare? How about this electron right here? That electron's going to see 11, a charge of 11 for the proton count, times, again, -1. And let's say that's still just 1 away, so that's divided by 1 squared, which is 1. So that would be 11. What about my second level? This electron right here. So that electron right there, that's still going to have a charge of 11 times -1 divided by, and then that's going to be twice as far away, so 2 squared, that's going to be 4. So it's going to be 11 over 4. If I look at this one, well, that's going to be even further away. So that would have a 11 times -1 divided by 3 squared. Now, suddenly that's 11 over 9. So we can see that as this distance goes up, this is getting pretty extreme. But also notice that this sodium, because it has 11 protons, its second layer, this is my second layer, is able to beat out the second layer of the lithium atom. And so this is going to be a good explanation for why bigger atoms can hold more electrons. Lithium probably wouldn't be able to hold a third layer of electrons. The forces would just become so weak, those electrons would just leave. They would just vanish. So Coulomb's law is something we should be familiar with. We should be able to relate the radius with the force and the charges that are in an atom. Okay? So we should be able to see that the further away we get, our force drops off quickly. The higher our charges get, the bigger our force is going to get. And so we should be able to see that easily. And we're going to start to apply that right away looking at the photoelectric effect in the next video.